Okay, we have moved into section 3.4, and in this section, we want to talk about understanding the derivative as a rate of change of a function. The derivative really gives us the rate of change of a function. So going back to the definition, if we want the derivative of f at a specific value of x naught, then f prime of x naught is a limit as h approaches 0 of f of x naught plus h minus f of x naught over h. And only throw this definition back in there for you to understand that this tells us an instantaneous rate of change of f, right? Without the limit, this is the slope of secant lines. So it's telling us an average rate of change from a point x naught to a point x naught plus h, all right? But as soon as I take the limit, then I'm shrinking this h down to 0, and I'm trying to find the slope of the tangent line. That gives us an instantaneous rate of change of a function. And that's another way to think of what the derivative tells us. So the derivative is the slope of the tangent line, but what is that slope of the tangent line? It's the instantaneous rate of change of that function. So as a simple example, let's look here at example 36. The area A of a circle is related to its diameter by the equation A equals pi over 4 times d squared. We're all comfortable with A equals pi r squared, right? Well, r is 2d, so that's how you get pi over 4 times d squared. If r is 2d, right? Pi r squared would be 2d squared, would be 4d squared, so 4 divided by 4, we end up with pi r squared. But this is the area of a circle in terms of the diameter instead of the radius. So how fast does the area change with respect to the diameter at the specific instant when the diameter is 10 meters? So in other words, if I have this circle, A equals pi over 4 d squared, I'm asking for what's the derivative of that area with respect to its diameter, dA dd, right? A is a function of the diameter d. A equals f of capital D. So I want the derivative of A with respect to the variable diameter, d, dA dd. So that's a simple. You just use the constant multiple rule, leave the constant multiple in front. Pi over 4 is just a constant. Take the derivative of d squared as the power rule, 2 times d to the 2 minus 1, or just 2d. Simplify this, it's pi over 2 times d. So this is the derivative of the area of a circle, the rate of change of an area of a circle with respect to its diameter for any diameter of that circle. So we want to know what's the rate of change of the area of that circle when the diameter is specifically 10 meters. So the way I usually write that is I put a vertical line next to dA dd, and I say this says the derivative of A with respect to the diameter of the circle when d is equal to 10 meters. That just means plug in d equal to 10 meters. So that's pi over 2 times 10. And then just to show you the units here, we don't always worry about the units too much in Calc 1, but I just want to show you the units, right? Area is in meters squared, diameters in meters. So the rate of change of the area is meters squared of the area per meter of diameter. So you simplify this, when d is 10, you get 5 pi meters squared per meter. If you'd like to see what that is in decimal form, you plug pi into your calculator, 3.14159, etc., etc., etc. Round it off to 2 decimals and you get 15.71 meters squared per meter. So if I had a circle that its diameter was slowly increasing, say like an oil spill in the ocean, then what would happen is you'd say the area of that circle is increasing by 15.71 square meters for every meter that the diameter of that circle is changing, assuming my oil spill is perfectly circular, of course.